this class we are going to look at solid liquid separation. As I had mentioned before, immediately after a fermenter you have a solid liquid separator. There are different types of solid liquid separator, and solid liquid separation is performed in order to remove the cell debris, dead biomass, and precipitated media components and so on. So, we are going to look at these various types of solid liquid separating processes actually. So, if you look at removal of solids, as I said, this is the first step in the downstream. It is going to involve dead biomass, cell debris, suspended solids, undissolved salt, all these have to be removed first before you actually recover your desired product and purify your desired product. So, if it is a biocatalyst, like if you are looking at enzyme catalyzed biotransformation, you like to recover the biocatalyst, recycle it back into the bioreactor. So, again you need some sort of a filter or a membrane and so on actually. And so, there are two different situations when you are looking at a solid liquid separation. So, if the desired product is intracellular, then we have to harvest the cells, that means your product is inside the cell. So, you have to harvest the cells, lyse the cells to get your product out. If the desired product is extracellular, you are not bothered about the solids. So, what do? You actually filter the solids and then dispose the solids, because the liquid is what your desired product is. So, you collect the liquid, then you start recovering your product which is inside the liquid, whereas in the other case if it is intracellular, the desired product is inside the cells. Okay. So, one of the easiest solid liquid separation is called sedimentation. Okay. So, why does it happen? The solids settle down due to natural or artificially induced gravitational fields. It could be a natural gravitational field, or it could be because of a centrifugal force, the solids could be separated actually. So, particles have to be denser than the liquid, that is very important, and because of these density difference, that gives you a driving force. So, the settling time of the solid in this liquid depends on the physical properties of the solid and the fluid, like densities, viscosity of the liquid and so on, and the driving force is the difference between the two densities. So, what is the law which governs this solid liquid separation in a sedimentation, or it is also called settling? That is called the Stokes law. It is very simple, but it is quite powerful in doing certain calculations. We will look at some problems as we go along. And so, when a solid, freely suspended solid is settling, so there are many things that are happening actually. You have the buoyancy, you have the drag force, and then you have the gravitational force. All these three are taking place actually. Okay. So, the buoyancy, the gravity and the drag force. So, if you try to balance all these together, you end up with an equation which determines the velocity at which the solid will move down. This is called the terminal settling velocity. Okay. That is called the terminal settling velocity, which is just because of the gravitational force. So, you have to balance all these forces and you end up with an equation like this. The terminal settling velocity is equal to d square, that is the diameter, d is the diameter of the solid, mu is the viscosity of the solid, rho s is the density of the density of the solid, and rho l is the density of the liquid, and then you have the g, the gravitational force. Okay. So, the velocity, that is the terminal settling velocity, depends upon the diameter of the solid. So, larger the diameter, faster it will come down, inversely proportional to viscosity. If the viscosity of the medium is high, the settling velocity becomes low, and the driving force here, rho s minus rho l. So, if I have a large difference, then I will have a large settling velocity. If you have small difference, I will have a small settling velocity. So, the most important point you have to consider is the solid should be moving at a very low velocity, that means at a very low Reynolds number, that is very important. Generally Reynolds number should be in the order of less than 1. Okay. How do you calculate Reynolds number? The equation for Reynolds number you all may be knowing, okay, is equal to d, that is the diameter of the particle, okay, then u, that is the velocity at which the particle is moving, rho is the density, okay, that is the liquid density, mu is the viscosity of the liquid. Okay. So, du rho by mu is what is Reynolds number, and that should be generally less than 1. So, you need to see whether your Reynolds number is less than 1, otherwise this particular equation is not really reliable to use. Reynolds number has to be less than 1. Okay? That is very important. When you have settling taking place in a centrifuge, then instead of G, which is the gravitational force, you will have omega square r. Okay. What is omega square r? Omega is your angular rotation of the centrifuge, that is radians per second. R is the distance of the solid particle from the center of the axis. Okay. Further the particle away from the center, you are going to have high driving force, that is why you have r here, and larger is your RPM, larger will be your settling velocity. So, you use it this particular equation when you are using a centrifuge for settling your solids, and you use the previous equation if you are using normal gravitational force for settling of solids. So, instead of omega square r, you are going to have G, otherwise the equation remains the same. So, as you can see, G is always fixed, whereas if I am doing settling in a centrifuge, I can keep increasing my omega, that means I can keep increasing my RPM, so that I achieve very high settling velocity. Okay. Whereas in the normal gravitational type of settling, I will not be able to achieve such very high velocities. So, this is how a settling tank looks like. The settling tank is a huge tank, the feed comes in, the slurry and the solid, you give enough time inside, so that the solids will settle down, and then the bottoms will contain concentrated solids, whereas the top will contain clear liquid. This is used very common in effluent treatment plant to remove the initially solids that are present in the effluent. This is a very simple setup, you do not require any energy for this, you do not require any agitation or aeration and so on. So, it is very cheap. Only thing is you need to give sufficient time inside your tank, so that the solids get settled. So, if you know the solid property like a density and diameter, if you know the density and viscosity of the liquid we are using, generally in an effluent treatment you will have water as the liquid. So, you know the density and viscosity of water, we can calculate the velocity, and we can, once I know the height, I will know the time for which I need to allow the slurry to stay in the tank, so that the solids will settle down very effectively. Okay. So, it is quite simple, it is quite a powerful equation, although the equation is very simple. We can use it for calculating the time for which the slurry has to stay inside the settling tank. Okay. Flocculation, what is flocculation? Sometimes very fine particles they do not settle down at all, that is because there is a lot of electrostatic forces, like particles with 0.1 micron, they always remain away from each other because of these electrostatic forces. So, they do not agglomerate at all. So, you want to separate them. Filtration may be a difficult option because the particle sizes are very small. So, you resort to something called flocculation or agglomerization. So, basically here you have to make the electrostatic forces, neutralize the electrostatic forces, so that the particles come together and form larger flocks. Then it may be possible for it to settle down inside a settling tank. So, basically what you do here is you add something called a flocculating agent, so that it breaks the electrostatic forces and allows the particles to come together and form larger particles which settle down. That is what is done in flocculation actually. Okay. So, you can remove it as a flake, or it can be like a flock, like a precipitate basically, but there is a difference between precipitation and flocculation. In precipitation, the concentration is larger than the solubility of the solid in the liquid, that is why it precipitates, whereas in flocculation we have finely divided solid present inside the liquid, they are not coming together because of the electrostatic repulsions. So, you add a flocculating agent, allow them to come together and collide and then form larger particles which can settle down, that is what happens here in flocculation. Okay. So, they will clump together, or they will also flock together. So, sometimes they can float at the top of the liquid if the density of the flocks or the bulk density of the flocks are less than the liquid density, or they can settle to the bottom of the liquid if the density of the flocks are much larger than the density of the liquid, or they can be easily filtered, because when the particles are very fine it may be very difficult to filter through a filtration unit. Of course, we can go into some nano filtration, but that is very expensive. So, you can make it into larger flocks, then it becomes easy to use a very normal filtration unit to filter it out. That is what is done in flocculation. Okay. So, basically you are doing a charge neutralization and bridging. These are the things that happen, mechanism by which flocculation takes place. Basically, the flocculant neutralizes the charge on the particle. So, hence there is no repulsion between particle and particle, or they form a bridge between two charged particles. So, the particles become larger or flocks. Okay. So, instead of flocculation we can also call agglomeration, we can also call it coagulation. So, you add a coagulating agent, or you add a flocculating agent, you add an agglomerating agent. So, they are all synonymous to each other actually. Okay. So, there are a lot of flocculants that are used, synthetic chemicals, natural chemicals and so on, that are generally used to break this type of charges on that actually. They are generally used quite a lot in water treatment plant, they are used in environmental plant when you are remediating the effluent that is getting discharged and so on actually. So, what are these flocculants? They are generally multivalent cations like aluminum. Aluminum has got aluminum chloride, iron, calcium, these are all multivalent, Mg2, Fe3, Ca2, that sort of salts. Okay. That sort of inorganic salts that are used. So, they will generally neutralize the charge that are present on the small sized particles. Okay. Or sometimes you can add acids, bases, even simple electrolytes, polyelectrolytes, polyacrylamide. So, all these are added and they are all called flocculants actually. Okay. So, it can be long chain polymer flocculants like polyacrylamides. So, basically they do not have charges on them like acids or bases actually, or like your inorganic salts. So, the problem with these flocculants are the fouling, they can foul your membrane, number 1. Number 2, they become impurity. If you are interested in the solids particles, then they are impurities that will be present in that with the solid particle. So, if you, then it becomes very difficult for you to separate them out. If liquid is your desired product, then there is no problem, but still flocculants can sort of foul your membrane. There are chemical flocculants and natural flocculants. Large number of flocculants are available in the market like aluminum chlorohydrate, aluminum sulphate, calcium oxide, iron chloride. In natural, if you look chitosan, papain, so many things, so many different types of material could be used as natural flocculants actually. Polyacrylamide, sodium aluminate, sodium silicate. So, large number of flocculants are available but of course, they also start becoming an impurity. You need to think of removing them if they are very toxic, or you discharge them into the open with the solids that you are throwing it out actually. So, the solids will also contain these extra chemicals which you are adding to destroy the charge neutralization. So, what are the various steps in flocculation? So, you may add the flocculants with the solid, okay, or you may add them separately. So, suppose we have the feed with the suspended solid, you may add the flocculant, okay. Then when you add the flocculant, if the solids become very heavy, the flocks become very heavy, then they will all settle down. So, the liquid is removed. So, it is a sort of a batch process, you know, this is at time 0, and then you are adding flocculant at time t1, and then at the time t2 you can remove the liquid at the top and the concentrated flocks or agglomerates at the bottom. Now, analogous to that, if the flocks are lighter than the liquid, then it may float. So, at time equal to 0 you take your feed, then you add your flocculant at time equal to t1, and then after some time the solids which are floating or skimmed off or removed at the top, and the liquid is at the bottom, which is clear. So, both the approaches are possible depending upon the flocks that are formed later or heavier or lighter than the liquid. Now, there is another method that is called air flotation. So, what you do is again the particles, suspended solids are very light, they do not agglomerate because of the charge. So, you bubble air. So, the air acts as some sort of trapping the solids, and you end up having froth which will have a lot of concentrated solids on the top, because air is there, generally the density will be lower. So, on the top you have froth with all the solids trapped, and which can be skimmed here, and the clear liquid can be collected at the bottom. So, here you require air here. The advantage of this method is you are not adding extra chemical and contaminating the setup, you are just bubbling air into it, so that the solids are the fine particles are trapped in the air, which can be skimmed out. So, this is much more advantageous than adding a flocculant or adding a coagulant. But of course, in very large systems that may become a problem. So, it is much easier to add a coagulant. In water treatment especially, they generally use a coagulating agent to do. Okay. Now, we saw sedimentation, we saw flocculation and so on. Now, the next one is filtration. Okay. You must have all seen filtration from very early ages. So, the slurry is passed through a cloth, metal, polymer, fibers or candle with fine pores, solids get retained and the liquid flows through. That is a very simple thing. Now, there are two types of filtration system. One is called the surface filter. When you have a solid sieve or a solid piece of cloth or metal or ceramic, like your Buchner funnel or belt filter or rotary vacuum drum filter, all these come under surface filter. So, the solids are retained on the surface and the liquid flows through. That is why the name is called solid surface filter. So, similarly, we have something called depth filter. Here you can have a long tube which may contain solid particles or sand or gravel. So, when your slurry flows through, the solids hit these various solid particles and they get trapped and the liquid flows through. So, this is a typical example is sand filter. Here we cannot collect the solids, whereas in the surface filter we can collect the solids, and if you are interested in the solids, then surface filter is always better, whereas in the depth filter we cannot recover all the solids. Okay. So, the first type the residues can be collected intact, the second type does not permit. So, the sand filter, like you have a bed of sand where liquid flows through with the solids get trapped by the sand, especially this is used in water treatment. Okay. So, this is a very simple setup, it is very cheap setup. Rainwater harvesting, they use a sand filter. So, the sand just traps the solids that are flowing through, and generally this is used if the concentration of the solids are very low, whereas this first method is used if the concentration of solids are much higher. Okay. So, in a filter you can have this type of design, this is a horizontal design, or this is also called dead end filter. So, the feed slurry comes in, there is a filter cloth or filter medium, here it is called filter medium, it could be a metal, ceramic, and so your cake is formed here and the liquid flows through, liquid is collected here, right. Or you can have a plate and frame design. So, you have a frame, you have a plate, porous plate through which your filter medium is placed, slurry flows through, cake is formed, it is removed here and then you collect the liquid. So, this is a batch process, because after some time the cake accumulates so much that you need the flow of the liquid goes down and down. So, you need to stop it, scrape out the cake and remove it. Also in this system also you need to stop the filtration, remove the plate and frame, again remove the cake that is formed and again restart the whole process. This is a candle filter. So, there is a candle which is, it could be a ceramic or a metal with porous holes. So, the liquid slurry is outside. So, the liquid flows through, the solids are retained on the surface and the pure liquid comes down. So, this is generally used in water treatment, even in households you might see. Okay, so, you can have pressure type of filtration, you can have vacuum type of filtration here. So, pressure means the slurry is forced on top of the filter medium under pressure, whereas in the vacuum, a vacuum is used at the bottom, so that the slurry is sucked and solids are retained and the liquid flows down. So, both the techniques are commonly used, the pressure type and the vacuum type. So, if you are using a pressure type, we can achieve very large pressure gradients, whereas with vacuum you get only a delta P of 1 bar. So, that is the main difference between pressure and vacuum type filtration. Okay. You also have something called rotary drum filter. So, there is a big drum, it is porous and there is a vacuum inside. So, the slurry is sucked. So, the solids are coating on the drum, liquids go inside, this drum keeps rotating slowly. So, the solids are settling and coating on the top of the drum, cake is formed here. So, we can wash the cake in case there are some impurities which are washable dissolved in water, then that gets washed and sucked inside, then we can dry it and finally the cake can be cut here. So, again the drum is empty or clean, which dips into the slurry and again a cake is formed. So, this is a continuous process. The rotary drum filter is a very continuous process, because you are forming the cake when the drum is dipped inside your feed slurry. So, the cake that is formed can be washed here, so that you can remove the impurities that are formed on the top and then you can dry it and then finally you can cut it and recover all the wet solids and again the drum dips inside. So, this is generally used in lot of pharmaceutical industries. So, you are removing the solid from a slurry, you are washing the solids, partially drying it here, because of the vacuum here it gets partially dried, it is cut and collected. Then later on you may go into further downstream like complete drying or some modifications or so on actually. So, these rotary drying type of filters are generally continuous operation, unlike the previous filters which we saw, they are all batch operation. Okay. Now, two types of filtration you need to know: the dead end filter, the liquid flows, the slurry flows like this. So, you have the cake that is formed on the top and the liquid is collected. So, the problem with this type of filtration is after some time the cake thickness increases and increases and the flow of the liquid becomes negligible, you need to stop it and you need to scrape off all the cake, clear the top of the filter medium, so that again the filtration can be started. Whereas in the cross flow, the liquid is, the slurry is flowing in this direction, okay, cross, it is flowing tangential to the filter medium. So, cake formation is very low. So, this type of accumulation of cake is less. So, this is much more advantageous, because the cake formation is very low and so the liquid and the filtration is always much more when compared to the dead end type of filtration. Okay. So, these are the two types, one is the dead end, another is the cross flow filtration. Okay. So, what are the advantages of cross flow? Liquid removal rate, a good liquid removal rate is achieved, because you are not allowing it to form large thick cakes, and in a dead end thick cakes make the liquid flow less and less, and after some time the liquid flow can totally stop actually. And the feed always keeps moving on top. So, we can take it and do further processing, unlike a thick cake, thick and dry cake, where we cannot do further processing unless you put it again in a slurry. And the solid content of the product slurry may be varied over a wide range, and we can even use this for fractionating particles by size. So, we can have initially a filter, a cross flow filter with very fine holes, and then we can have bigger holes and so on actually. So, we can have a fractionated type of solid separation, whereas we can't do that in a dead end type of filtration. Then you have this belt filter. What happens is, this is a long belt, this can be hundreds of feet long, and the feed slurry is charged here, okay, the feed slurry is charged here, and then it moves along between two rollers. Okay. So, the water is squeezed out as they go through these rollers. Actually, there are two different belts and the solid is between these two belts, and because of these rollers the water gets squeezed out, and then at the end of it the dry solids fall off. Okay. So, initially it is entering as a wet solid and it gets squeezed and squeezed between two belts. So, water gets removed and finally it falls out as dry, and again the belt rolls. So, we can achieve continuously removing the liquid from the solids as well as to make the solids little bit dry. Later on we can go to a dryer to completely remove the moisture. Okay, that is possible actually. Depth filter I mentioned, that is called the sand filter or the depth filter. So, you have a bed, you have pebbles which are of larger size, then you have aggregates which are of smaller size, then you have the sand which are of much smaller size. So, for example, rainwater can flow here and the particles that are present or the impurities that are present get captured because it hits the solid material and gets captured, and the liquid has to flow through a tortuous path. So, the solids are removed and we get the filtered water. So, generally this is practiced in rainwater and you do not need any mechanical moving parts actually. So, how do they remove these solids from the liquid in this sand filter? The direct collision, van der Waals forces, surface charges, diffusion. So, all these are present in a sand filter, and that is how the solids are removed from the liquid. Generally sand filters are used if you have low concentration of solids, whereas the other type of filter, surface filters, are used if the solid present is much larger. Okay. Now, generally filtration is based on Darcy's law. We are going to spend some time on Darcy's law and this is what filtration is based on, where the velocity of flow of the liquid through the bed is directly proportional to the pressure difference, inversely proportional to the viscosity, and BD is the bed thickness. So, if the bed thickness is higher and higher, your velocity goes down. If the bed thickness is lower and lower, velocity goes up, and the driving force plays a very important role. K is a constant, it depends on the so many factors, the compressibility and so on actually. But this Darcy's law is valid only if the Reynolds number is less than 5, but it is a very useful equation. We can use this for many calculations. We will look at some problems later actually. Okay. Commonly used filter medium: filter paper, woven material, cheesecloth, polymer fibers, woven glass, non-woven material, sintered perforated glass, perforated metals, ceramics, synthetic membrane. So, almost anything can be used. You can perform filtration at high temperature, room temperature and so on. Okay. After filtration we have centrifuges. This is called a tubular bowl centrifuge. There is a bowl here. So, your feed slurry comes and is pushed upwards because of the centrifugal forces. The solid hits the wall and it gets stuck to the wall and the clear liquid flows through. So, after some time there will be build up of solids on the surface of the bowl. So, you need to stop the centrifugation and scrape off these solids. This is called tubular bowl centrifuge because it is tubular in shape and there is a bowl. You have disc stack centrifuge. We have lot of discs here. Okay. So, the liquid is the slurry is flowing from the bottom and it hits these angular discs and the solids get thrown out and the liquid flows upwards. So, because of these discs the solids get thrown out and hits the wall and they are collected at the corners of this wall. So, the solids are collected at the corners of the wall, the liquid flows through. So, that is called the disc stack centrifuge because we have discs. We can also use the centrifuge for filtration also. If the outer walls of the centrifuge are porous, then when the slurry hits the wall, the liquid will come out through the holes, the solids will be trapped inside and it will form a coating and slowly the solid will start building up. So, the centrifuge can also be exactly looking like a filter. So, the liquid comes out, the solids keep accumulating along the walls of the cylindrical centrifuge and they start building up. So, today we saw different types of solid liquid separating units like sedimentation, flotation, air flotation, filtration, two types of filtration, the depth filtration as well as the surface filtration, and then we looked at the centrifugal systems like bowl centrifuge, disc centrifuge, centrifugal filter and so on actually. So, we will do some problems in the next lecture. Thank you very much.